So what exactly are customers thinking while they are trying to understand which are the features within any given product they should be buying or not? So presume there is some product which is available in the market that you want to go ahead and buy. Why would you buy it or why would you not buy it? So how do the features within that particular product influence your decision? The product can be something as simple as groceries that you're buying, or maybe some digital gadget that you're buying, maybe a new smartphone, maybe an iPad, whatever it is that you're buying. It's the features of that particular product that ultimately influence your decision whether to buy or not to buy. So let's look at some very basic methods to analyze this and to try and understand as to why a certain product would sell and or why it would not sell, and what features would impact the sales decision or the purchase decision at the consumer's end. So here is my little very basic code that I have gone ahead and I have written. And what this is basically talking about is it's a logistic regression model, and there's a very simple data set that we have. And before I go ahead, let me just clear out all of this. So there's a very simple data set that we have. We just call it D. If we go ahead and look at this particular data set, we have certain columns over here. That is the APC, which is basically the actual purchase count, whether a person has bought that particular product or not. F1.R is the feature 1, the feature 2, the feature 3, and then there are certain ratings for these particular features, as you can see. So let's go ahead and import this very simplistic data set into R, and let's see. So you can see the data set over here. It says 500 observations of 6 variables. Very simplistic data, nothing fancy, not even big data, just a demonstrative set. And let's look at what we can do with this. So basically what we have is we have a dependent variable that is the actual purchase count that we have coded as the APC, the actual purchase count. And this dependent variable is what we are going to regress, and we are going to show that regression along with other independent variables which we have picked up from consumer survey and certain concept surveys that we launched. Now, the most important factor that we need to go ahead and look at is which model would fit and which model would be most significant to go ahead and predict whether a particular retail consumer would buy our product or not. So the purchase intention is quite different from liking a particular feature. So somebody might go ahead and like a particular feature. So as you can see over here, for feature 1, there are different ratings over here. The rating 4, the 5, 0, 0, again 5, 5, 5. So these ratings have been given by consumers who were given a consumer survey or a concept survey, and they went ahead and rated certain features of that product. But that does not necessarily mean that they will buy that particular product. Now over here, somebody has gone and rated most of the features as 0 besides one particular feature, that is F5.R in row 4. But this individual has gone ahead and bought the product. Similarly, there are certain folks who've gone ahead and rated it say as 2 over here, and nothing else has been rated, and they've not gone ahead and bought the product. So there is different permutation combinations over here, and let's see which one of these influences and which one is significant. So that significance testing is the basic criteria that we have to fit a particular model, to see whether a particular prediction model goes ahead and is able to predict whether we want to buy a certain product or not. So there is no graphing of residuals, and as far as If you know what residuals are, then that's good enough. Otherwise, that's not required. So there is no graphing of residuals being done because the diagnostic plots might not be helpful in this particular assessment of this model, as the response variable does not take many values. The response variable, which is the actual purchase count, is taking only two values, either 0 or 1. It's a binomial variable. So in such a situation, doing a plot or doing some diagnostics with regards to residuals or plots is not really recommended. It will not give us much results. The other thing that we want to look at is the Akaike coefficient, and this of course if it is smaller, the better the goodness of fit for a particular model. Then we would also look at the confusion matrix. The confusion matrix is basically comparing the classification capability between GLMs, that is generalized linear models, and what we have over here is generalized linear models with with logit link as the link function and binomial as the family. So we compare percentages of misclassification. So percentages of misclassification is what we are looking at, and once we've done that, we will be able to say that which particular model went ahead and said had a better true positive rate and did not have a very high true or also a true negative rate. So basically what happens is, if a model goes ahead and looks at all of these variables, let's look at row 1, and the model says I'm looking at these variables which are, one is 0, one is 4, another one is 2, then there are again 2 4s over here, and the model says that I am going and predicting 1, which means that a customer who has rated these different features in this manner will go ahead and purchase that particular product. But in the actual situation, presume in place of this 1 we've got a 0, then that model is not good enough. So that model's probability of predicting or classifying what is actually happening in the real data set or in the real world is not good enough, and that kind of a model we will not find it to be significant. So that is what this basically means, this entire piece over here. And then of course we will go ahead and do a significance test, which is the Hosmer-Lemshaw test, or called the Hoslim dot test, to compare the p-values or the probability values. So the lower the p-values, the better the goodness of fit for individual individual models. For individual variables, what we look at is, we look at the Wald test values. So the Wald test values are nothing but the Z statistic and the associated p-values which are there, which are denoted by this probability of Z within the summary. So these p-values are to be lower than 0.05. That is what we've set as our LOS, or the level of significance. We could look at different levels of significance, and accordingly we could read the p-values in a different manner. But as of now we are looking at 0.05 as the level of significance. So after analysis of all of these, we have found the model. So I've just gone ahead and left this blank. I have not filled this up yet. So we will see which particular model we find to be significant in explaining, most significant in explaining the variability of the dependent variable, which is the actual purchase count, due to the various independent variables. So thus we infer that our consumers have preferred certain features. So those are feature 1, 2, 3, or whichever one is there. We will get to see that later. So we don't necessarily know right now, because we've not created the models, we've not compared the models, we've not looked at the models for significance. Okay, so this over here is nothing. The first command is nothing. It is just R showing that that's the location of my data, and it's gone ahead and imported that CSV. We've already done that. We go and attach that data set. We get to see, okay, fine, there is some error which is mentioned over here, because I've already gone ahead and attached that data set already. So we can just ignore this. This is not to be considered right now. So these are our independent variables. I have already shown you as to what the independent variables are. These are F1, F2, F3, F4, F5. These can be absolutely anything. So any variables for which you've gone ahead and gathered inputs from your consumers in a survey, in a market survey, those variables can be coded over here. And the dependent variable is binomial oblique dichotomous, and that's the reason we are doing a logistic regression. Otherwise we could have gone ahead and done a linear regression. The logistic regression is not a linear regression, and then there's a lot of theory involved, which I obviously am not addressing over here. Now, the dependent variable is a dichotomous or a binomial variable. It takes on two values, that is 1 and 0, and rest of our variables are categorical variables which are taking values between 0 to 5. Yeah, so the Likert scale values are there. Now, the first thing that I want to do is I want to look at this data set, and the annual purchase count, I want to code it as Y, because I want to go ahead and do a few other things with that particular variable. So that's what I'm doing, and I'm looking at Y now. So my console over here shows the values for Y. It is showing me that the first observation is 1, then the observation is 1 again, and 0 and 1 1 1, and that is exactly what we get to see over here: 1 1 0 1 1 1. Now we go ahead and create a factor from Y, but I think I'll skip this step for now. I straight away go to my first model. So my first model is M1, so I just call it M1. It's a generalized linear model. Why it is a generalized linear model, even though I'm saying it's logistic regression, and it does not it does not necessarily follow a linear relationship, because we have gone ahead and modified the model in such a manner by putting a logit function within it, that we have generalized it or made it akin to linear models, even though internally it is not a linear model. So the relationship between this particular variable, that is the actual purchase count, sorry, I had mentioned annual purchase count earlier, it is the actual purchase count, and the other variables within the data set, which we don't get to see over here because I am using this code to regress against all the variables, all the independent variables. Otherwise those variables are seen here in the data set. The relationship between the actual purchase count and these variables is not a linear relationship, and that's the reason we call it a generalized linear model and not a linear model. If it was a linear model, we could have just gone ahead and coded it in this particular manner. Okay. So the family is binomial. The method which is being used within this thing is logit, that we don't necessarily have to expressly mention over here. That is the default for binomial. Now let's look at the summary of this particular model, and let's see what all inputs we get in the summary. Okay, sorry. We go ahead and so this is what the summary looks like. And to read the summary, first it says call, and it is mentioning what exactly our linear GLM is all about. It gives us the formula, that is annual purchase count has been regressed against all of the variables, independent variables present in the data set. The family is binomial, data is D. Then it gives us the Devine's residuals. So Devine's residuals are basically residual values which display as to how much a particular model deviates from a null model. A null model would be a model wherein there would be only a intercept value or a beta 0 value, and there would be no independent variables. So from that kind of a model, how much does our particular model deviate? So, and this of course is these are the quantiles or the quartiles for our Devine's residuals. The next that we see are the coefficients. The coefficients are basically the beta values of the independent variables and of the intercept, that is beta 0. So under estimate, we get to see all the coefficients for different independent variables, that is f1, f2, f3, f4, and we also get to see the beta 0 value or the intercept value, the intercept coefficient, which is minus 6.8297. The next we get to see is the standard error for this particular coefficient, and the z values are nothing but the estimate divided by the standard error, which gives us the z value, and basis this particular z value we have probabilities on the z scale or the p values. Now ahead of these p values we see significant codes. Now if you look at this down here, those similar significant codes are there. When you see nothing over there in front of that particular p value, which means it is significant at say about 10% level of significance, and that is not what we are looking at. What we are actually looking at is 0.05 level of significance. So this particular value over here, which is for f2 point r, is not necessarily a value that we want in our model, because this will reduce the overall significance of our model. And how do we go ahead and judge the overall significance of our model is by looking at the null deviance values and the residual deviance values. So the null deviance is basically the deviance or the deviation that our model displays when there are no independent variables within the model, and with 499 degrees of freedom. So 499 degrees of freedom is nothing but whatever is my n, what is seen over here, which is the 500 observations, those 500 observations minus 1. So that is basically the degrees of freedom, n minus 1. And this 494 degrees of freedom is 499 minus how many independent variables do I have over here. So this number of independent variables, that is, and the null deviance and the residual deviance, we look at these data within the processing of this particular data set. And then we have the Akaike information criteria, coefficient. Akaike information coefficient. The AIC has got a certain relationship with the residual deviance, which is mentioned over here, but I might not cover that here. But what we need to look at and what we need to be aware of is the AIC value, which is 142.25 over here, should be lower for the model that we go ahead and choose as the significant model amongst all the models that we'll test. So the AIC value is one particular indicator which will help us understand that which model is best comparing amongst models. Okay. Now, as seen in this particular summary, the variable f2r is not significant. It has a p-value which is higher than most other p-values. And so we drop this variable from the model. So the next model that we create, which is seen over here, the M2, we've gone ahead and dropped the F2. The F2 is not there. We just have the F1.r and the F3.r. But before we go and create the next model, let's go ahead and create a correlation matrix for the independent variables and all of the independent variables. So just to understand, because there is a lot of amongst folks who are just either starting to understand some of these things, or the layman perspective is that a high value of correlation also usually means causation. That is not true. In certain cases you might see a high value of correlation, but again that does not necessarily mean that one variable which has shown a high value of correlation will also be the reason why a certain other variable or a dependent variable is showing higher values. So that causation might not happen. So let's look at, we've uploaded a certain library called CorePlot. And what we are basically doing is we have created this particular variable, that is core_m, and that entire data set has been fed into this particular variable. Now what it will do is it will just pick up the names from here, the column names from here, and it will show us the correlation for all the observations. So it will show us a point value for all the observations. Now presume within this column f1.r I have 500 observations, their correlation with this second column or my second variable, that is f2.r, and also their correlation, the f1.r, with APC. So all of these would be correlated and shown to us in a matrix format. So let's look at this particular plot and what it looks like. So this plot has come up over here. Let me increase this size. Okay. This does not look very impressive because there's not very, there's not much to be seen here. Let's export it into a PDF and let's see if that is much better. Now, where do I want this? I want it on the desktop. Yeah. So that is okay. Let me just call it the core plot. Let's look at this. Okay. Now, if you look at this particular core plot, there are these variables on top. That is the actual purchase count, the F1, F2, F3, F4, all of them. This is the correlation scale. So anything close to 0 is low correlation, or those two particular variables do not have a very high correlation value, or anything close to 1 or -1. On the extremes of this particular scale, whether in red or blue, towards the 1 or the -1 means there is a high correlation. So the highest correlation which we can see, and that's the reason it's been plotted in a in a darker font, is the 0.93 between f2.r and f1.r. So that's okay that these two independent variables are showing a high correlation. So what we will probably have to be cognizant of is that we do not go ahead and show interactions of these variables, of these two variables, in any of our models that we want to explore. Because if we do that, then again, that will probably be wrong. So that's one takeaway that we can have from this particular matrix. And then looking at these figures over here. So looking at the figure of 0.21, which is the correlation between f5.r and actual purchase count. And then 0.14, which is f4.r and actual purchase count. And then looking at 0.53. So obviously f1.r and actual purchase count are much more highly correlated when as compared with f4.r and actual purchase count. So that is one thing that we get to see over here. But again, our regression might show different results, might show different variables to be significant. So we can't necessarily make any significant judgment from this correlation plot. So let's look at this second model wherein we've gone ahead and dropped one particular variable, and let's look at the summary now. Now, as seen in the summary, all of these variables are showing us significant p-values. So we don't want to drop any variables going ahead as of now. And let's just say for this particular example, we stick to these two models and we don't create any other models. Okay, now let's look at something called the odds ratio for independent variables. So what exactly is the odds ratio? The odds ratio, and let me describe it in further detail. Okay, let me look at that document later and probably read out few things from there. The odds ratio is basically the odds of a particular variable within the model being more significant or impacting the dependent variable while keeping all of the other variables constant. So let's say, let's forget for a minute that we have any other independent variables within the model, and let's say we only have f1.r. Then the odds ratio which is achieved over here by these two lines of code, that is 9.12, is the odds of influence by this particular variable on the dependent variable, or the outcome, the probability of the dependent variable ending up being 1 or ending up being the expected value. So the probability is, let's say 9.12 for f1.r, that the dependent variable would end up being or end up taking a value of 1, which is that a particular observation would be a yes, a purchase has happened, an actual purchase has happened, versus an actual purchase has not happened. So in simple terms, that is what the odds ratio is. We also want to look at the Hosmer-Lemshow test. Now the Hosmer-Lemshow test would give us p-values and a chi-squared value with certain degrees of freedom. Now basis these p-values, we will go ahead and judge whether a particular variable is significant within our model or not, and further if it is not, we can go ahead and drop that variable. Also, we can look at the entire model and see if that particular model is significant or not. So over here we see that the p-values are 0.9551 and 0.9514. Well, these are okay, so nothing much we can do over here, because these models are highly correlated. These models do not have much difference amongst them. That's why these p-values are not showing much of a difference, and we can't really go ahead and do much right now. So let's say next thing we look at is the confusion matrix. The confusion matrix is the percentage of misclassification. Now like I stated earlier, presume the actual in the actual data set, when you, for a particular consumer, you go ahead and track and you see that that particular consumer had gone ahead and given these ratings, and the consumer went ahead and bought your product also. So the actual purchase has happened, versus somebody who did not purchase, and your model predicts otherwise. So over here, say your model predicts 0, and over here your model predicts 1. So that would be misclassification. So the percentage of misclassification or the probability of misclassification is what we are looking at from the confusion matrix, and we are looking at it for these two different models, that is M1 and M2. We can also look at the confusion matrix for within variables to try and understand whether certain variables are significant or not. But the preferred method is to look at the confusion matrix for different models. The confusion matrix can be created with different packages within R. So within the caret package, the confusion matrix can be created. It can also be created with other packages, but what we've done is we've just gone ahead and used the base package for this. And now here we are assigning values from the fit, from the predicted fit, which is given by M1, our first generalized linear model, into a variable which is pred underscore M1, which is just the prediction of M1. And we also want to see that whether these values are greater than 0.5. So that 0.5 is the threshold we have chosen for going ahead and classifying the particular event as a purchase or not a purchase. So presume that over here I get something like 0.55, over here I get something like 0.57, over here I get something like 0.58. So all of these are classified as purchases, or that particular product being bought by a particular consumer. And presume this I get as 0.49 over here. So this will be assigned a 0, and this one could be 0.30 or whatever, a value less than 0.5. So we'll go ahead and assign it a 0, and we will see the purchase has not necessarily happened. So that fit is being coded over here. And the next we go ahead and see the confusion matrix, the table which has been created. So over here what you see is in these two columns, the headers are false and true. So the false means that actually these are the values of zeros which have been predicted. So 80 values of zeros have been predicted, and what you see on the left side is the denotes the let's say it denotes the actual zeros. So false, how many times did our model predict a zero? That is 80 times, whereas in reality also there were 80 zeros. Also our model predicted zero or false 13 times, whereas in reality in the actual data set they were for corresponding to those particular observations they were 13 ones. So this is the misclassification which has been done by our model, or the wrong prediction which has been done by our model with regards to the zero, or with regards to the purchase not actually happening, but our model going ahead and saying purchase actually happening, but our model going ahead and saying that it has not happened. So this 13 is considered as a false negative. So this false negative is the 13 which I am showing you over here. Now when you look at this particular column, the true, the 13 and the 394, so how this needs to be predicted is, how this needs to be understood is that our model went ahead and predicted that a purchase has happened, or a true value or a 1 value is what our model went ahead and predicted, or a yes value, whereas the actual data set shows that it was a 0, which means it's a false positive as far as we are concerned. The FP underscore M1 over here, which also shows the value 13, because both these values just happen to be 13. So it is not necessary that you will get the same values for the FP or the FN. That will not happen. But in this particular model, it has come out to be that way. And then of course our model went ahead and predicted that 394 purchases have happened, or 394 ones are there, or 394 yeses are there, or the event of interest has been predicted by our model 394 times, which is also the reality in the actual data set. If you see, there are 394 ones or yeses or actual purchases. So that is the true positive, which is 394, and the true negative, which is 80. So okay, so again we've gone just to calculate the percentages and get few other things done. We've gone ahead and calculated the length of this, and once we look at that value over here, we'll get we'll get 500 as the length, or rather 500 is the total number of the observations on which the confusion matrix has run this particular test. Okay, now we are wanting to calculate the percentage of misclassification, which is denoted as, the formula is false positive plus false negative divided by n. So this n is what we've computed over here, that is 500. The false positive and false negative values, we've gone ahead and input those manually over here. I am sure there's some way of coding it in, but I have not done that. It gets coded in if you were to use some of those packages and use the confusion matrix which is provided there in Caret or other packages, but I have not done that. So this is the percentage of misclassification. This percentage of misclassification comes out to be, okay, I'll have to first go ahead and input these values. Yeah, that is done. Now the percentage of misclassification is 0.052, which is 5.2%. So it's only 5.2% cases in which our model is going ahead and misclassifying. Let's also look at two other values. One is sensitivity and the other is specificity. So how many times was our model specific? To what extent was our model specific, and to what extent was our model sensitive? So the true positives divided by the true positives plus the false negatives gives us the sensitivity value, and the true negatives divided by the true negatives plus the false positives gives us the specificity value. Yeah, so those values we've got. Now let's look at the confusion matrix for the other model, and because we get to see the true positives, the true negative, and false positive and false negative over here, and these are same as our earlier model. What we can infer, and that's the reason I'm not going through this entire code, is that the values given by the confusion matrix would be the same. So those values are actually exactly the same. So I'm not going into this. Now comparing the null and residual deviance within a model to see if the model by itself is significant. Now within the model, like I stated earlier, the null deviance, and if we go to the summary and look at it, this is for model 2 that we are looking at the summary. The null deviance is nothing but the value which we would get as the deviance value if there was absolutely zero independent variables and there was only the intercept. Now presume in a condition or actual, in practical scenarios or in the real world, how would this actually happen? So presume you go ahead and spend some money on creating a particular product, and you go ahead and seek inputs from your consumers to see as to whether this product has got, say, n number of features, and out of those features which one is significant or not, and presume all of those results come back as zero. So your consumers say that we don't necessarily care about any of the new features that you're incorporating, and whatever is there earlier in your product, maybe it's just the brand equity or whatever earlier features are there, due to that reason we will go ahead and purchase happens. So that intercept value or the beta 0 value, that coefficient is the only thing which is available in that particular model, and that is what the null deviance value is. And of course the residual deviance is how much this particular model deviates after it has got all of these variables, independent variables in it, and basis these two, the AIC value is calculated. And the lower the AIC value, the better the model is. So the AIC value that I have over here is 140.41 for model M2, and the AIC value that I have for model M1 is 142.25. So even though I stated that these two models are not very different, but still we can see a slight difference in the AIC values and the preferences for model 2, which is absolutely okay, because the model 2 is also showing all the independent variables to be more significant and adding value to this particular model, or being more significant while influencing the dependent variable versus the model 1 which had f2.r, which was not significantly influencing the dependent variable. And whereas when we saw the correlation matrix, we could see that for f2.r also the annual purchase and the actual purchase count, there was a high level of correlation. So that does not necessarily show in the significance results for the regression model. Now we can look at these differences between the null and the residual deviance, and then we do a ANOVA between the models. So we do a chi-square test and an ANOVA between the models. So what that shows us is that there is a difference. This is the difference between the deviance levels, and of course the M2 is again being preferred over here, the model M2. So this is the analysis of deviance table, which has a chi-square distribution with how many degrees of freedom? That is -1 degrees of freedom, which basically means that our model 2 is showing degrees of freedom 495 and model 1 is showing degrees of freedom 494, and that's why it's got a -1 degrees of freedom for this particular chi-square test. So this brings us to the end of testing the significance of the model. We've already gone ahead and fitted the model and seen as to what kind of predictions are happening, and we've gone ahead and seen that the difference in predictions is not much, but that is coming out to be for these two particular models. If we were to further go ahead and create interactions, or if we were to look at data sets which were larger in size, there's just 500 observations over here, we would definitely find that the confusion matrix or the percentage of misclassification would also differ, and then we would have a distinct reason, or a rather much more significant reason, to go ahead and prefer model 2. So this model 2 GLM M2 is what we are actually preferring. Presume you've gone through this entire activity and you want to go ahead and now report your findings. And how would you do that? So basically go ahead and compile a notebook in R. So it says compile notebook over here. It gives you 3 different options. It gives you a HTML option, a PDF option, and a Word option. So let's look at the HTML first, and what else can we do with it. You can also go ahead and publish this HTML to the internet straight away. You don't need to, okay, execution halted because of Pandoc is giving some challenge. Okay, let me see if I can do this in some other format. Otherwise, I'll have to go and look through my code as to why it's not. Let's see if this gives me a. No, there seems to be a challenge. No, there is no challenge. It is going ahead and creating the Word document at least. So it's showing me the date today. It's showing me it's Monday 11th May. It is giving me the time around 10 o'clock. It is showing me as to who's gone ahead and created this document. That's me. Fine, this is good enough. And what I could do is I could simply convert it into PDF from here, save it on my desktop and have a look at it. Or I could also go ahead and convert it into PDF from within R also, and I can show that to you. So this is what my report would look like. So if there are some other things that I want to input, I can go ahead and do that. It's showing me that I have gone ahead and read in the data. I have attached that. It is also showing me the factor that I did not create because probably I could not, I saved it earlier. I shouldn't have done that. Okay, and it's showing me the summary of my GLM model 1. It is showing me the, I have gone ahead and uploaded that particular core plot library. I've gone ahead and chosen that library. I put it in, I've gone ahead and uploaded it in the memory of R. I've gone ahead and created that core plot. But where exactly is that core plot? And this is the challenge I've had with Pandoc and LaTeX lately. My GG plots and my certain other plots don't necessarily come into the document. I don't necessarily know why, but I'll probably have to look at that. So this is what I could use as my, not necessarily as my report to be sent to a client or something, but at least a ready reference from which I can create my further data sets, or I can create my further documents. Okay, so any questions that you have, you go ahead and post them in the comments, or you can write to me. My email ID, does that show up over here? It doesn't. I don't know why. Okay, and there's another website that I have that I've gone ahead and put few more things over here. It's called R for Beginners. And myself, I am not very experienced with R as of now. So yeah, it depends. If you see something over here which you think is useful, you can always get in touch with me. We can probably discuss a few things. And yeah, these are some of the plots that you get, some of the very basic plots that you get out of ggplot2 and those other fancy packages that we have for graphing. But most of them don't necessarily show up in the Pandoc and LaTeX. I don't necessarily know why. Any which ways.